Okay, so this is section 6.3, which basically is separation of variables, also logistic growth equation, and homogeneous equations, which relate are equations that initially cannot be solved by separation of variables, but if you make a appropriate substitution, you can have it work. So we're going to start off with the easy ones first here. So problems 1 through 12, which we have two from that section, find the general solution of the differential equation. So the general solution means that there's no initial conditions, and you're going to end up with an arbitrary constant somewhere. So problem 3 says dr ds is equal to 0.05 r. So our two variables are r and s. S is the independent variable, and r is the dependent variable. And so we're going to separate them. We want to get the r over here and the ds up here. There's no s by itself. So basically what we do is we multiply by ds, both sides by ds, and we divide both sides by r. And what that will give us is dr over r is equal to 0.05 ds. And now that we have separated the variables, we have r here, we have s over there, we integrate both sides. And dr over r is the natural log of the absolute value of r. The integral of ds is just s. And we add our arbitrary constant c at that point. Again, each one of these integrals is going to give us an arbitrary constant, but it's just going to be a constant so they can be added together. So rather than doing it twice and adding them together and creating a new constant, we just add one constant at this point. And typically we want to be able to solve for r, in this case, explicitly, which means it's r is equal to something. So we're going to have to take, we have to change the left and right hand sides to the exponent of a natural exponential function, and which means e is the base. And I'm just going through my stuff here, so be ready. Okay, so if we take e to the natural log of the absolute value of r is equal to e to the 0.05s plus c, so this whole right-hand side is the exponent. Again, when you take e to the natural log of the absolute value of r, it just becomes r. And then the right-hand side, we can use the properties of logarithms to break that up into two parts. And this just becomes an arbitrary constant, which we could call C1, but we're just going to call C because, you know, up until the point we actually apply it, the initial condition, it doesn't matter. So this is just our usual exponential relationship, our exponential equation. So we get r is equal to c times e to the 0.5s. Our second example in the simple general solution of separable linear equations are x, which is number 6, x times y prime is equal to y. So we're going to replace y prime with the other representation, dy dx. Then we'll say, okay, we're going to, since we want to solve this, we're going to rewrite this in differential form, dy divided by dx. And now we separate the variables. So let's divide by y and multiply by dx over x. So what that's going to move, it's going to move the x's to the right-hand side and the y's to the right-hand side. So what we get is dy over y is equal to dx over x. Okay, so I'm going to move these to the side. This goes from the denominator to the numerator. This goes from the numerator to the denominator. And so now we can integrate it because we have them separated. So we just integrate like we normally do. So the integral of dy over y, of course, is the natural log of the absolute value of y. The integral of dx is the natural log of the absolute value of x. And we add our arbitrary constant. Now again, we want to explicitly solve for y, so we're going to make the two sides the exponent term of the thing like that, and when we can do the same thing here. We can break it up into two parts. On the right hand side, and we can call that c. Well, e to the natural log of y is equal to y. E to the natural log of x is equal to x, and we have e to the c, which we're going to just call c again. So it just ends up, it's going to be x, y is equal to x times c times x. And that's it. Problem number 16 is really just like we've been doing, except now we apply the initial condition. So we're going to find the general solution, then we're going to apply the initial condition. And notice, if you look in problems 13 through 22, most of them have the argument x or t or whatever as 0, but it doesn't have to be. So initial, you might think, oh, it always has to be t equals 0, but it's just really, initial condition is maybe a good word, maybe not. Anyway, number 16. 2xy prime minus the natural log of x squared. So it's the natural log of x squared equals 0. So one thing we can do is you can use the properties of logarithms to rewrite this term. And so we can bring the 2 outside, and we get 2 times the natural log of x. Okay, and then you can see we could cancel the 2's out, divide everything by 2, and we get xy prime minus the natural log of x equals 0. And now we're going to, let's move that to the other side. And let's change y prime into dy dx. And now what we're going to do is we're going to separate the variables. So all we have really on the left-hand side is dy. We're going to divide by x multiplied by dx. So we'll have the natural log of x over x dx. So now everything is separated. And at that point we can then do the integration. So we have the integral of dy is equal to the integral of the natural log of x over x dx. So how do we solve the integral on the right-hand side? The one on the left-hand side, of course, is just y. So, you know, the derivative of the natural log of x is 1 over x, so 1 over x dx. So if we choose u in this case for the right-hand side to be the natural log of x, then we take du, which is 1 over x times dx. You can see this part here is going to be du, this part's u, and that becomes a polynomial in terms of u. So we can transform this equation to u times du. This is u, this is du. Now we can integrate. Let's integrate both sides. So we get y is equal to u squared over 2 plus our arbitrary constant. We substitute back in, and so we get y is equal to the quantity, the natural log of x, quantity squared divided by 2 plus c. So this is our general solution because we have our arbitrary constant. We have solved explicitly for y. So to find the particular solution, we look at the initial condition, which says y of 1 is equal to 2. So what it means is we've got this coordinate pair, x equals 1, y equals 2. We could say that, or we could say x equals 1, y equals 2. So anyway, so we can then plug that in to this one point. What this gives us is a family of curves, all separated vertically by a constant. And this saying it goes through this point specifies which one of those curves out of the family it is. Okay, so y equals 2 when x equals 1. So we have the natural log of 1, the whole thing squared divided by 2 plus c. And the reason they choose 1 is because the natural log of 0 would be undefined. So anyway, the natural log of 1 is 0. 0 squared is 0, so this term drops out. And we see that the arbitrary constant is 2. So now our particular solution is y is equal to the quantity, the natural log of x, quantity squared divided by 2 plus 2. This is our particular solution, which is particular to that one initial condition. And this is problem number 16. So 1/2 natural log. Okay. Just seeing what they do. Yep, they do exactly what I do. Okay, problem number 17. So write down the problem from the book. Y times 1 plus x squared times y prime minus x times square root. Now, I did this last time. I wrote the wrong problem down. I can't keep my eyes on the right thing. Okay, so that's the differential equation. And we have the initial condition, y of 0 equals the square root of 3. Okay, so what we want to do is we want to separate the variables. And let's see what we want to do. We're going to move this term to the right-hand side. Let's go ahead and change y prime to dy dx. So by moving it to the other side, the negative sign disappears. And we're going to divide by this, we're going to multiply by that, we're going to divide by that. And what we'll end up with is y dy divided by 1 plus y squared is equal to x dx divided by 1 plus x squared. So that's the separation of variables part. Again, this is there from there, multiplied by dx, gets it up here, divided by 1 plus x squared, moves it to the denominator, y dy, and we divide by 1 plus y squared. Okay, so we can now integrate these two separately. And they have, of course, they have very similar form here. Actually exactly the same form. So I'm only going to do one of them, and then we just duplicate it by changing the variable. So let's do the left-hand side. So we're going to let u equal 1 plus y squared, the total denominator. Du would be equal to 2y dy. So our original equation has y dy, so we're going to divide both sides of this equality by 2. And so we can substitute for y dy, we can put in du over 2. And we can do the same thing on this side. But let's just do the left side integral, and we'll just copy it over. So the left side integral becomes 1 over y, pardon me, 1 over u times du divided by 2, which we can factor out. The 2 in the denominator is just half. You get the integral of du over u, and that is equal to 1/2 the natural log of the absolute value of u. And if we substitute u back in, we get 1/2 the natural log of the absolute value of e of 1 plus y squared. Okay, so what we can do now is just do that to both sides. So we're going to do 1/2 the natural log of the absolute value of y. 1 plus y squared is equal to 1/2 the natural log of the absolute value of 1 plus x squared plus our arbitrary constant c. We haven't solved explicitly for y. So, but we can get rid of the 1/2 because if we multiply each term by 2, the arbitrary constant will become 2c, but it doesn't really matter what we call it. So we're going to multiply by 2, but we're just going to say c is 2c. Okay, now then we can raise each to the e to the natural log of the absolute value 1 plus y squared is equal to e to the natural log of the absolute value of 1 plus x squared plus c. And when we do that, you get 1 plus y squared is equal to, well, remember we can break this up into e to the natural log of the absolute value times e to the c. We just call that c. So we get c times 1 plus x squared. And we could solve for y explicitly, but it turns out they don't do that. But we can evaluate. So this is our general solution. So now we take the initial condition. Y of 0 is equal to the square root of 3. What that means is when x equals 0, y equals the square root of 3. It also means this coordinate pair is valid for this particular solution. So we get 1 plus y, which is 0, squared is equal to c times 1 plus x. Actually, that's the wrong way around. Okay, sorry. 1 plus the square root of 3 quantity squared is equal to c times 1 plus x, which is 0 quantity squared. So 3 square root of 3 squared is 3. And we get c times 1, so c is equal to 4. And so our particular solution is going to be equal to this, 1 plus y squared times 4 times quantity 1 plus x squared. If we multiply the 4 out, we get that, and then we can subtract 1 from both sides, and we'll get 3 plus 4x squared. And that is the final answer. Okay, the next problem is 22. And we're still in this particular solution thing. So what we have is this may not at first look like a differential equation. They've actually already separated part of it out. I think we talked about this in class. This is the equation that relates heat transfer rate to temperature. So if I were to rewrite this, we don't actually want to do this to solve the problem, but what we would have is this. So I divide both by dt. I move that to the other side, and you see that the rate of change in temperature with respect to time is equal to minus k times T minus 70. So if the temperature is greater than 70, this will be a positive quantity. If K is positive, then the change in temperature will be negative, so it'll be cooling off, and that's true. And if you go the other direction, if this T here is less than 70, you get a positive change in temperature. And it all goes towards 70 at some point. Okay, so since this is already setup, what we're going to do is we're going to just do what we did here, except I'm not going to divide by dt. So our two variables are capital T, which is temperature, small t, which is time. K is a constant, but that's based on the material, so as long as the material stays the same, this is constant. Okay, so if I divide by t minus 70, I get dt over t minus 70 is equal to negative k dt. So I now have the two variables separated. I have capital T here, I have small t there. So now I can integrate both sides. And I'm just going to move the k, negative k outside the integral sign because those are constants as far as this integration is concerned. So the right-hand side is just going to be minus k times t. The left-hand side, we're going to let u equal t minus 70. So du is equal to dt. So if I make that substitution, the left-hand side just becomes dt becomes du, and t minus 70 becomes u. And on the right-hand side, we have negative k integral of dt. So natural log of the absolute value of u, we get minus k times t plus our arbitrary constant. Now we substitute u back in, so we get the natural log of the absolute value of t minus 70 is equal to minus kt plus c. And what we want to do is we want to solve for t, so we're going to make each side of this equality the exponent of this result. And so this part just becomes t minus 70. The right-hand side we can break into e to the minus kt times e to the c, but e to the c just becomes c. So we get c times e to the minus kt. And if we solve for t, we add 70 to both sides, so we get plus 70. That goes to 0. So this is our general solution. It's because we have not evaluated the arbitrary constant. The initial condition to find the particular solution says that t of 0 is 140. Again, that means when x equals, in this case, when t equals 0, then, actually small t, not big T. So when time equals 0, then big T is equal to 140. Okay. So we're going to use this by plugging it into here. So T is 140 when T is equal to 0. So I get minus K times 0. E to the 0 is 1. So I get 140 is equal to 70 plus C. C is equal to 70 by subtracting 70 from both sides. And so my particular solution is 70 plus 70 e to the minus kt. And I could factor out of 70, so I get 70 is equal to 70 times 1 plus e to the minus kt. So when something's wrong. Why is it wrong? No, that's right. When t equals 0, this goes to 0. E to the 0 is 1, so we get 1 plus 1 is 2. 2 times 70 is 70. When t goes to infinity, this goes to 0 because we have e to the minus infinity. If you remember, the exponential function looks something like this. So when t goes to infinity, that, well, actually this function looks like this. And when t goes to infinity, that term goes to 0. And you had just 70, which is your final temperature. Okay, so that's it. Problem 36. So now we're moving into this homogeneous differential equation part. And so problem 36 is actually solving the homogeneous differential equation. So let's write it down. The equation is y prime is equal to x cubed plus y cubed divided by x y squared. So you can prove that it's homogeneous if you substitute in for x, if you put in, let's call it nt, and if for y we put in nt. And so if we did that to the right-hand side equation, we'd end up with nt, actually it's not t, I've forgotten what we do here. Hold on just a second. Okay, so what we do is tx, sorry. So what we do is for x, we put in tx. And for y, we put in ty. So you get tx quantity cubed plus ty quantity cubed divided by tx times ty squared. So if we multiply this out, you'll get t cubed x cubed t cubed y cubed divided by t cubed x y squared. And in this case, the t cubes cancel out, and you get x cubed plus y cubed over xy, which is, you know, it's some n value of n, t to the n. Well, n is 0 in this case because it's just the same original equation. So it is homogeneous. So there's a couple of ways of doing it. What we're saying is that we define this new variable, and so what we're going to say is, actually we're going to say y is equal to mu x. That's one way of doing it, or you could say that y over x is equal to mu. So either one of those works. In this case, this actually probably is better. So what we would do is we take our original differential equation and divide by y cubed, or x cubed. And we do that for both the numerator and the denominator. So let's just write this out completely. So what we would do is we would, in the numerator, we'd divide by x cubed, and in the denominator we'd divide by x cubed. And what that would do is this x cubed divided by x cubed would be 1. Here we'd end up with y cubed over x cubed. In the denominator, we'd have x times y squared over x cubed, which is, okay, so this becomes y over x quantity cubed, and the denominator becomes, well, the first one is x divided by x is 1. So what we have is really x, and then we have y squared divided by x squared. So all I've done is I've taken this y cubed and break it into x times x squared. So x over x is just 1. And in the denominator I have y squared over x squared, which is the same as the quantity y over x quantity squared. So this becomes 1 plus mu cubed divided by mu squared. Okay, so that's That's what that is. And if I take the derivative here, I'll see that y prime is equal to x times mu prime plus mu times x prime. So I can make that substitution for the left-hand side. So I get x mu prime plus mu x prime but x prime is just 1. We're taking the derivative with respect to x. So mu prime is equal to d mu dx, and x prime is just dx dx, which is equal to 1. And on the right-hand side, I have this 1 plus mu cubed divided by mu squared. Okay, so this is just, we get x mu prime plus mu is equal to 1 plus mu cubed over mu squared. But mu prime is just d mu dx. And what I'm going to do is I'm going to move this to the other side. So I get 1 plus mu cubed over mu squared minus mu. And if I combine these two with the common denominator, I can replace this term with just mu cubed over mu squared. So the right-hand side is 1 plus mu cubed over mu squared minus mu cubed over mu squared. You can see this is going to cancel out with that. And so the right-hand side just becomes 1 over mu squared. The right-hand side is x d mu dx. So now we can do separation of variables. So what happens is you multiply both sides by mu squared, divide both sides by x, and multiply by x and divide by, multiply by dx and divide by x. So divide by x, multiply by dx, that gives us that term. Multiply both sides by mu squared, and so we can integrate. So you get the integral of mu squared d mu is equal to the integral of dx over x, and here we get mu cubed over 3 is equal to the natural log of the absolute value of x plus arbitrary constant c. And then we make the substitution back again for mu, which was somewhere, but it was mu is equal to y over x. So what we get is we get y over x quantity cubed divided by 3. I'm just making the substitution in there, plus equals the natural log of the absolute value of x plus c. And so what I'll get is x cubed over 3 is equal to, I'll get x cubed in the denominator, so if I multiply that both sides, I'll get x cubed natural log of the absolute value of x plus x cubed times this arbitrary constant c. And then I could multiply both sides by 3 if I wanted to. I wanted to solve for y cubed. I'm not sure what we do. 36. Yeah, so I'll multiply both sides by 3, and I get y cubed is equal to 3x cubed natural log of the absolute value of x plus, well, 3 times c is just, we can just call that c. So we have c times x cubed. And that's the correct answer. So that's one way of doing it. The other way of doing it is, if we go back to the original equation, what was that? We had this substitution that y is equal to mu times x. So when we look at the original equation, we get y prime is equal to, and again, y prime is going to be equal to mu prime times x plus the derivative of x is going to be 1 times mu. So that's using the product rule. Derivative of the first times the second plus derivative of the second times the first. So we can do that. I'm going to make that substitution here in a second. Let me finish writing the equation down. So we have x cubed plus y cubed over xy squared. So now we can make this substitution. We can make that substitution here, that substitution there. So we get x mu prime plus mu is equal to x cubed plus y, but for y we're going to put in mu x and cube that. So I'm going to use that substitution. I have x times y, but y is equal to mu x. And I square that. Okay, so what can we do? Well, I think we can simplify the right-hand side, but let's go ahead and write it all out. So we get x cubed times plus x cubed times mu cubed. Just cube each one of those separately and multiply them. And then here we'll have x times x squared, which will be x cubed, and then we get mu cubed right there. So you can see that these x's, since they're in all terms, can be canceled out. So we get x mu prime plus mu is equal to 1. So they don't go to 0, it just becomes 1. 1 plus mu cubed over mu, so actually that's mu squared, not mu cubed. So it becomes squared, squared. And I think that's where we ended up last time. Let's go back. Yeah, there it is right there. X mu prime plus mu is equal to that. So you go through the whole same thing at that point. So we can either make the substitution that mu is equal to y over x and rewrite the original equation in terms of y over x, or we can do it the other substitution. Okay, this is problem 42. Some of you may have already tried to watch this. And I don't know why I quit in the middle of it, but I did. So we'll do it, and we're actually going to do it two ways. We're going to do, okay, hold on a second. I was thinking of what's happening. I put my book down here, and I had it on my keyboard, and it was showing control. I didn't really know why that was going on. So there's going to be two ways. We're going to do it first using the rewriting it as y over x and put it in terms of y over x, which we're going to call nu. And I'll do the same thing to get the differential equation that I'm dealing with. And then we'll integrate it because we get the same differential equation no matter which way we do it. This is our initial condition. So what I'm going to do, instead of doing it this way first, actually let's do it that way first. So I'm going to multiply this out. So you get y squared dx plus, and you get x squared dy, and then we get x times y times dy. So you get xy dy. Okay, now I'm going to add a page here to the left, to the right. And the two substitutions we make are that y is equal to nu x, and that when we take the derivative of y equals nu x, we get, so dy, differential, is x d nu plus nu dx, using the product rule for derivatives. So we can then plug in, so we have negative y, which is nu x, and we square that, we multiply it by dx. So we're doing this term right here. And then we have x squared times dy, which is x d nu plus nu dx. So that's that term. And then we have x times y, which is nu x. So x times y, which is nu x, times dy, which is x d nu plus nu dx. And that equals 0. Then you multiply everything out. So we'll get negative nu squared x squared dx from the first term. Here we'll get x squared times x, which is x cubed. So we get x cubed d nu. Here we get x. I don't know why I'm doing different. Well, no, that's right. Okay, then, so we get x cubed d nu. Then we get nu x squared dx. From the second, x squared times nu dx is nu x squared dx. Then we have these terms. We'll have x times x times x, which is x cubed. We have nu, and all times d nu. X times x times x cubed. One. Okay, the second one, we get x times x, nu times nu, so we get nu squared x squared dx. That equals 0. Okay, now we are going to take the terms that involve dx to one side and the ones that involve d nu to the other side. So let's move dx to the right-hand side. So we're going to have what remains on the left-hand side is x cubed d nu plus nu x cubed d nu. Okay, that comes from this term and that term. Everything else goes to the other side. So this will become positive. So we have nu squared x squared dx. Then we have nu x squared dx. So it's a minus. And then we have nu squared x squared dx, which is going to be, well, actually these two are going to cancel out, but I'll go ahead and put it in here. So this will be negative nu squared x squared dx. Okay, so that cancels out with that. And the right-hand side, we can factor out an x cubed. So we get x cubed d nu. And that's multiplied by 1 plus nu. On the right-hand side, we get negative nu x squared dx. And then we can separate variables. So we're going to move all the stuff involving nu to the left-hand side. So we'll get 1 plus nu over nu. So we divide both sides by this. And on the right-hand side, we get negative dx x squared divided by, so this, we've already divided by that, so that's gone over here. We just have x squared dx, and we divide by x cubed, which x squared divided by x cubed is just 1 over x. And so this is my, oh, I forgot the d nu here. I forgot that right there. So this is my separable equation. Okay, now, what I'm going to do next is I'm going to go back and we're going to work it the other way. So let me just cover that up. Cover that up. Okay, the other way is to rewrite the differential equation in this terms. So all I've done is I have multiplied, actually all I've done is I've just moved this to the right-hand side. So I get positive y squared dx, and then divide by dx. And I get, and divide by this, and I get dy dx is equal to y squared over x times x plus y. And this is not separable, but it is homogeneous. So what I can do is I can take the original equation and multiply by 1 over x squared. Because what I'm trying to do is rewrite it in terms of y over x. Because y over x is nu. You know, before we said y is equal to nu x, so we can also say that nu is y over x. Either way, same thing. So we multiply the numerator and the denominator by 1 over x squared. This will become y over x quantity squared. This will become 1 plus y over x. Okay, and then we make the substitution that, well, this is to show that it's homogeneous, which it is. And then you could put in nu for this, and yeah, okay, that was proving it's homogeneous. So then we can go over here and I guess this one here. Okay, so there we go. And y is equal to nu x. So if we take the derivative with respect to x, so we get y prime is nu times derivative of x with respect to x, which is 1, and then the second one is this derivative with respect to x times x, v prime times x. So you multiply that out, just switch these two terms. So y prime, which is y dx, is equal to x nu prime plus nu. So the y prime part becomes x nu prime plus nu. To the right-hand side, it becomes nu squared over 1 plus nu. Okay, then nu prime is d nu divided by dx. So all I did here was subtract nu and what did I do here? Found the common denominator. So I take nu squared over 1 plus nu, which is that, and I multiply this by 1 plus nu so that I get this common denominator of 1 plus nu. In the numerator, you get nu squared minus nu squared. Those cancel out, and you just end up with negative nu. So I end up with nu over 1 plus nu is equal to x times nu prime. But nu prime is d nu dx. Divide both sides by x, divide by this, which gives you the reciprocal. So if you move this to the numerator and that's the denominator, by moving it to the other side, you get the same equation. That's the point here. So we get the same differential equation. Okay, now we have to solve it. So to solve it, we integrate. Now, one thing you can see is that I can create two fractions out of the 1. So I'll get 1 over nu plus nu over nu. Which, of course, this is just 1. So the integral of 1 over nu d nu is the natural log the absolute value of nu. The integral of 1 is, in this case, is nu, not x, because we're integrating with respect to nu. And that's equal to minus the natural log of the absolute value of x plus c. Okay, so that is, make sure I'm doing this right. So what I can do is I can, yeah, we have, it's a little tricky, but, so we can also say c is equal to the natural log of c. So it's kind of going the other direction. The reason I'm doing that is so I can put all this stuff together using the properties of logarithms. So what I'll do is I'll move all this stuff to the right-hand side. So I'll get negative the natural log of absolute value of nu minus natural log of x plus the natural log of c. And when you combine all those, you'll end up with the natural log of c And because these are negative, you divide by them, so you get 1 over natural log of c over nu times x. And I dropped the absolute value sign, which they do in the book. Okay, at this point, we can, do we want to make the substitution yet? No. So we're going to take e to the nu is equal to e to the natural log of c over nu x. Okay, e to the natural log of something is just that something. At that point, we can substitute in. So remember, nu is y over x. So we get e to the y over x is equal to c over y over x times x. And so the x's cancel out, and you get c over y. So if we solve for y, it's not exactly solving for y, but what we'll do is we'll move this to the numerator on the left-hand side, and this will become ce to the minus y over x. So if you multiply both sides by e to the minus y over x, you'll get e to the 0 here, which is 1. 1 times y is y. You get c times e to the minus y over x. So that's the general solution. And then you have the particular solution, which uses the initial condition. So you go all the way back to the beginning. And it says when x equals 1, y equals 1. So we're going to plug that in. Okay, so y equals 1 when x equals 1. So 1, 1. E to the 0, that's e to the negative 1 power. So you'll get 1 is equal to c e to the minus 1 power, which just says that c is equal to the positive 1 power. If you multiply this by e to the first power, e to the negative first power times e to the first power is e to the 0. And so you get 1, and you get e to the 1 times 1 is e to the 1. So that's just e. So that's what c is. So we get y is equal to e times e to the minus y over x. This is e to the first power, so you can combine these two and you get e to the 1 minus y over x. And that's the answer in the book. Final answer. Okay, this is problem 43, which is our second example of homogeneous equations. And we're just going to assume it's homogeneous, so we don't have to go through that again. Okay, so we have x secant of y over x plus y times dx minus x dy. So we're going to do this one differently in that we're going to say that y is equal to mu x. And so if you take the derivative of these in a differential standpoint, it's still the product rule. But what you end up with is you'll end up with v times, or b mu, you'll end up with mu times dx plus x times d mu. So the first times derivative of the second, but the second times derivative of the first. So we're going to use that for that substitution right here. And then we use this substitution for y. So the original equation becomes x, because we don't substitute in for that. Secant of y, which is mu x divided by x, plus y, which is mu x, the whole thing times dx minus x times dy, which is mu dx plus x d mu. So those are using those two substitutions in the original equation. And then we multiply everything out. So we have x. No, let's simplify that. So the x's cancel out, which is the important thing. So if we take x secant mu times dx, we get x secant mu dx. X. Then we have mu x dx. Ux dx. Then we multiply here, so we have negative mu x dx. And then we have this times that, which is negative x squared d mu. Now what happens a lot of times in these problems is you get something that cancels out. So that's one thing. The second thing is that a lot of times you'll have a common term. So you'll see we have x here and we have an x there as well. We actually have x squared. So if we divide by x, in both cases we end up with the secant of mu dx minus x squared, just not x squared, just x, because I've divided by x. So I get x times d mu equals 0. Now, this equation we should be able to use separation of variables. So we'll move the second term to the right-hand side, so it becomes plus positive x d mu. And then we'll divide by x and divide by secant. So we get dx over x is equal to dv over the secant of mu. So we have x on the left, mu on the right. I'm going to move this to the other side. I'm going to switch sides. And secant is 1 over cosine. So 1 over secant is cosine. So this becomes cosine of mu dv is equal to dx over x. So this part I just moved from the left to the right hand side. This one, 1 over the secant is equal to the cosine. Okay, so now we can integrate them. The left hand side with respect to mu, and the right hand side with respect to x. And what do we get? Well, the integral of the cosine is the sine, so we get the sine of mu is equal to the natural log of the absolute value of x plus our arbitrary constant c. And let's see if they actually solve for x. No, they actually solve for x instead. But let's go ahead and substitute back in. Mu is equal to y over x. So we get the sine of y over x is equal to the natural log of the absolute value of x plus c. And if we want to solve for x, we can take we could solve for x explicitly, which is what they do in the book. So actually, I'm going to move this. We're going to do it the other way around. So we get the natural log of x, sine of y over x. I've got plus c, but I moved to the other side, but I'm just saying negative c becomes plus c. And then you can, let's go ahead and apply the initial conditions. The initial conditions were that y of 1 equals 0. So that means when x equals 1, y equals 0. So we get the natural log of the absolute value of 1 is equal to the sine of y over x plus c, okay, sine of y, which is 0, over x, which is 1. So that's the sine of 0, sine of 0 is 0. The natural log of 1 is 0, so you get 0 is equal to 0 plus c, or c is equal to 0. And so our particular solution is the natural log of the absolute value of x is equal to the sine of y over x. If I want to explicitly solve for x, I can do this, raise each side to the power. Actually, I'm really not solving exclusively for x because there's x on both sides. So this is the answer the book gives you. X is equal to e to the sine of y over x. Okay, next problem is 50, which is an Euler solution. So we're actually going to use spreadsheets here. So we get dy dx plus 6xy squared is equal to 0. And they want us to use Euler's equation and then solve it analytically and compare the results. So let's do it analytically, and then we'll set up our spreadsheet from that. So if we subtract the second term from both sides, we'll get this. And then we can separate. So we get dy over y squared is equal to negative 6x dx. And we can integrate both sides. And this is the same as y to the minus 2 dy. And this is just the same. So when we integrate that, we'll add 1 to the exponent. So we'll get y to the minus 1 power divided by negative 1. The right-hand side will become negative 6, the constant, times the derivative of x dx, which is x squared over 2. And we'll add our arbitrary constant c. And then what do we have? Well, we have 1 over y. Negative 1 over y is negative 6 times x squared over 2 plus c. This is going to reduce to 3. So we get, if we multiply by negative 1, we'll get 1 over y is equal to x squared, 3x squared plus c. And if we get the reciprocal, we'll get y is equal to 1 over 3x squared plus c. Okay, so that's the analytical solution. That's our general solution. Now we're going to apply the initial condition to get c. So the initial condition is, from the book, when x equals 0, y equals 3. So we get 3 is equal to 1 over 3 times 0 squared plus c. 3 is equal to 1 over c, therefore c is equal to 1/3. And I'm just making sure I'm doing it right here. This is number 50. Okay, yep, c is 1/3. So plug that back in. We get 1 over 3x squared plus 1/3. And if we multiply the numerator and the denominator by 3, we get 3 over 9x squared plus 1. So that's our solution. So now we'll write that down so that we have it when we want to plot these things. 3 over 9x squared plus 1. So we're going to plot the function in Excel. We're going to actually calculate it in Excel. So let me open Excel. Okay, so I'm ready to start sharing with you now. Okay, so here's Excel. And if you remember Euler's method, we're going to have a column that's x, a column that's y, a column that's y prime, and a column that's delta y. And I'm also going to have a column which I'm going to put right here, which will be y calculated. That'll be from the analytical expression. And they want us to start at x equals 1. And when x equals 1, y is equal to let's see. So what is method with step size 0.1 to approximate the particular solution of the initial value problem at the given x value? Okay, so that's true. So the corresponding y value, if we plug that into x equals 1, we get, let me just pause for just a second, I need to check something. Okay, I just want to make sure I was using the right initial condition. So we do plug into the analytical expression to get the initial value. And, oh no, I see what it is. So we're going to start at 0. And we're going to calculate between 0 and 1. We're going to do it analytically and numerically. Okay. So our initial condition is 0, 3, so that makes sense. The y calculated value, that's what we had from the integration, and the result was 3 divided by 9 times x squared plus 1. So that's the slope at x equals 0. I mean the slope, that's the actual calculated y value. And it should end up being 3 if I did that correctly. Yes, it did. Okay, so that's the calculated value. Y prime is from the expression for the derivative. So the expression for the derivative says that dy dx is equal to minus 6xy squared. So we say y prime is equal to negative 6 times x, which is this item, times y squared. Okay, so that's the slope, which is 0 initially because x is 0. And this is delta y. And delta y is just equal to y prime times delta x, which in this case is 0.1. And then we set the next value of x to just be the old value of x plus delta x, which is a2 plus 0.1. The new value y is equal to the old value of y plus delta y, which is right here, the previous step. This should just copy over. This and these two should copy over as well. Okay. So what we're going to do is we're going to now take this whole row and copy it down far enough that we get down to x equals 1. Okay. So this is our x value increments in equal amounts, equal to 0.1 according to the problem. This is the y value calculated using the Euler's method. This is the one calculated from the analytical solution. So what we see is the exact answer is 0.3 as far as y at x equals 1, and the Euler solution gives us 0.2622, which is correct. And so if we wanted to look at the error between the actual solution and the so what we do is we take the that's the incorrect. This is the correct. So that's the difference. And so there's no error to start with because we're starting at the same point. And as we go along, the error increases. Is that correct? There's a decrease. Actually, it's actually bigger to start with, and then it gets less, which is interesting. Did I do that right? Yep. Okay. That's interesting. Anyway, that's the answer. This column gives us the results as far as the analytical solution. This is the estimated solution, and then the difference between the two. Okay, this video is going to be doing 55 through 58 because they're all basically the same kind of problem. So what we're supposed to do is to look at the description, and then we'll come up with an equation that fits the description, and then we'll look at the curves to see which one It's that as far as slopes are concerned. So 55 says the rate of change of y with respect to x, that means dy dx, is proportional. So we can put some proportionality constant, the difference between y and -4. So that's the difference. So what we see, what can we say? Well, the slope equals 0 when y is equal to 4. So let's look at those pictures and see if there's any cases where the slope is equal to 0 at y equals 4. And so if we look at figure B, we can see that and it says verify your results, but we're not going to verify our results. We're just going to look at it. So to me it looks like B because of this particular case. Okay, 56 says the rate of change of y with respect to x is proportional to the difference between, no, actually that's incorrect. It's not B. So if you look at those figures again and see, are there anywhere y equals 4 the slope? So it's actually A is that. That's the case. B is the second, so that's A. So if you look at A, you'll see that at y equals 4, you go along horizontally, you see that all the slopes are 0 when y equals 4. So 56 is the same kind of thing. dy dx is proportional to x minus 4. So that is B, because the slope is 0 when x equals 4. If you look at B, you see that that's the only one that has a 0 slope. Okay, let's see, I'm screwing it up again. Okay, now we're going to look at some logistic growth problems. So we're going to start with problem 71, and it's, what are they asking for? Find the value of K, find the carrying capacity, find the initial population, determine when the population will reach 50% of its carrying capacity. Write a logistic differential equation that has a solution. Okay. So this is actually the final answer. And the numerator is always the carrying capacity, so that one's easy. So what do we ask? A, find the value of K. Well, K, if you look at the logistic growth function, it's general form. So if we go back and we look at the solution, which is on the bottom of page 427, it's minus K. So K is equal to 0.75. Not negative, it's 0.75. So on the bottom of page 427 it says y equals L divided by 1 plus B e to the minus KT. So K is positive. Okay, the second question is find the carrying capacity. Okay, so this was A. B, that's 1500. Because when t goes to infinity, you get e to the minus infinity, which is 0, so that term goes to 0, you get 1501, which is 1500. So that's another way of looking at it, but it's always the numerator. Find the initial population. Well, the initial population is when t equals 0. So what happens is we would get p of 0 is 1500 divided by 1 plus 24. Because when t equals 0, we get e to the 0. E to the 0 is 1, so we just have 24 times 1. So it's ultimately going to be 1500 divided by 25. So we make a calculator. 1500 divided by 25 is 60. So that's the initial. What's next? Determine when the population will reach 50% of its carrying capacity. So that's when P of t equals 750. I wonder if there's any rule of thumb here, or we could just have to calculate it. Okay, I don't see anything that says that. Special case, it's kind of like a half-life, but not really. It's a half population. So all we have to really do is we're going to have to solve for t. So we're going to have 750 is equal to 1500 divided by 1 plus 24 e to the minus 0.75 t. So what I'm going to do is I'm going to multiply by this and divide by that, or I can just say I'm going to switch the numerator here with the denominator there. So I get 1 plus 24 is equal to 1500 divided by 750, and I forgot some extra stuff here. 24e to the minus 0.75 t. Okay, and that's equal to 1500 divided by 750, which is 2. If we subtract 1 from both sides, we'll get 24e to the minus 0.75 t is equal to 1. Divide by 24, we'll get e to the minus 0.75 t is equal to 1 over 24, which is 1 divided by 24, which is 0.04167. And then we take the natural log of both sides. And the natural log of a number between 0 and 1 is always negative. So let's take the natural log of that number. So I get negative 3.178 is equal to negative 0.75 t. So t is negative 3.178 divided by negative 0.75. So t is 4.2. And I guess probably units are years, maybe. Does it say what it is? It says units. Okay. Okay, let me just check to make sure everything's good shape. 4.2374. Yep. Okay, so that's that, and the final one is write the differential equation. And if you go back to page 427, you can see if you have what was the variable name? P. Okay, P. So you'll have that the PDT is equal to K, which is 0.75, times the dependent variable, which is P, times 1 minus Y, which is P, divided by L. And L is the carrying capacity, which we said was 1500. So I'm just checking the answer, and that is correct. Okay, so this is K, this is Y, this is Y, this is L. The 24 comes from the initial conditions, which so the initial conditions would be that P of 0 equals 60. Okay, so we're on problem 73, another logistic growth problem. So I'm looking it up here. So in this case, 71 we're given the equation, now we're given the differential equation. So the differential equation is that the PDT is equal to 3P times 1 minus P divided by 100. Use the equation to find the value of K. Well, K is this number here, so K is equal to 3. B is find the carrying capacity. Well, that's the denominator of that term, so we'll say L is 100. C, use a computer algebra system to evaluate to graph a slope field and determine the value of P, which the population growth is the greatest. Okay, so C we're going to skip, but D, what we would say is that if we took the derivative of the derivative and found out the value of T where this is maximized, then we would be able to answer the question. So what we do is take the derivative with respect to time of the first derivative. So we take the derivative with respect to time of the right-hand side also, which is going to be, well, let's multiply this thing out. So we get 3p minus 3p squared over 100. So when you take the derivative of that, you'll get 3 minus, okay, so we'll have 2 times 3, which will be 6p over 100. So actually that's the result here. So if I take the derivative of that, I'll get 3 minus 6p over 100. And we want to set that equal to 0 to find a maximum or minimum. So let's multiply both sides by 100, so you get 300 minus 6p is equal to 0, because you get 300, 100s cancel out, 0 times 100 is 0. So we get 6p is equal to 300 by moving this to the other side. It becomes positive, switching sides. And so p is equal to 50. So when the population is 50, then the slope is a maximum. Is that correct? 73. Okay, I was looking for it here. 4p equals 50. So that's correct. And if we wanted to do the derivative of the derivative, we'd see that if you took the derivative of 3 minus 6p over 100, you'd get negative 6/100. It's a negative, which means it's concave down, which means it's a maximum. Okay, next problem is 76. Find the logistic equation that satisfies the initial condition. So 76. So the equation is dy dt is equal to 1.2y times 1 minus y over 8. And we have the initial condition that at t equals 0, y is equal to 5. So again, we don't have to solve the differential equation. We've already done that. What we do is we identify what we know. We know that k is equal to 1.2. So the carrying capacity is 8, 1.28. So we plug those in there, and we'll get y is equal to L, which is 8, divided by 1 plus b, e to the minus 1.2t. So the only thing we don't know is b. So that's what we use the initial condition for. So what this means is when x equals 0, y equals 5. So we plug it in. 5 is equal to 8 divided by 1 plus b times e to the minus 1.2 times 0. Of course, e to the 0 is 1, so this just becomes 5 is equal to 8 divided by 1 plus b. So we need to solve for b. So if we multiply these two, do a cross product, we get 5 plus 5b is equal to 8. So we get 5b is equal to 3 because we subtract 5 from both sides. And we get b is equal to 3/5 by dividing both sides by 5. Okay, so B is 353. So the final solution here is going to be equal to y is equal to 8 divided by 1 plus 3/5 e to the minus 1.2 t. And that is the correct answer. Okay, our final logistic growth problem is problem number 79. So this is a word problem, but we should be able to figure everything out. It says a conservation organization releases 25 panthers into a game preserve. So that means when t equals 0, p is 25. So those are initial conditions. After 2 years, the population is 39. The Florida Preserve has a carrying capacity of 200 panthers. Write a logistic equation that models the population of panthers in the preserve. So logistic growth says P is equal to L over 1 plus B e to the minus KT. And we know that L is 200. So we have two unknown constants for this particular special case. We have B and we have K. Well, we can use these two conditions to find those. So the first one we do is P of 0. It means T equals 0. So we get 200 plus 1 plus B e to the minus K times T, which is 0. So it doesn't matter what value K is. This becomes e to the 0, which is 1. P of 0 is 25. So we get 25 is equal to 200 divided by 1 plus B. Now, if we cross multiply, we'll get 25 plus 25B is equal to 200. Subtracting 25 from both sides, we get that. And then dividing both sides by 25, we will get that B equals 7. So our equation now becomes P is equal to 200 divided by 1 plus 7e to the minus KT. So we still now have still one constant. We're going to use the second one to figure that out. So the population at 2 years is 39. So we put t equals 2, population 39. So we're going to solve for k from this equation. Well, let's rather than cross multiplying, we're going to switch the numerator and the denominators from the two sides. So we get 200 divided by 39. So 200 divided by 39 is 5.13. So this is equal to 5.13. So if we subtract 1 from both sides to get just the exponential term by itself, we'll get 4.13. 5 minus 5.13 minus 1. And then we divide both sides by 7. So we have 4.13 divided by 7, which is 0.59. Okay, take the natural log of both sides. And the natural log of that number should be negative because it's between 0 and 1. 0.59 is between 0 and 1. So we get negative 0.528. And here we get negative 2k. So k is equal to negative 0.528 divided by 2 by negative 2. By negative Negative 2 gives us 0.2638. So that's our, and let me just make sure everything's right, 0.26, okay. So our final solution, taking everything into account, so the population is equal to, what is it, 200 divided by 1 plus 7e to the minus 0.26, we'll round off to 4, t. Okay, so that's our logistic, that's A, answer to part A. Answer to part B, find the population after 5 years. So all you have to do is plug, this is P of t, when t is equal to 5, all you have to do is just plug 5 into the equation. Just like that. So let's try 200 divided by the quantity, 1 plus 7 times e to the negative 0.246 times 5, close the parenthesis, and I get 65.6. So I'm just going to round up to 65 because let's see what they do. Well, they say approximately 70. I don't know why they round off that much. Okay. Excellent. When will the population reach 100? So we put population of 100 in there, we get 200 over 1 plus 7e to the minus 0.246 times t, and we solve for t. So we're going to switch the numerator and the denominators from the two sides. So this goes to the denominator, and this comes up to the numerator. Subtract 1 from both sides. Divide by 7. Take the natural log of both sides. So here we just get negative 0.264. Maybe that's where I got messed up. 264. T is equal to the natural log of 1/7. Natural log of 1/7. Again, it should be a negative number. Negative 1.94. So if we divide both sides by this number, I get 7.4 years. Okay, so that was part D, right? Logistic differential equation models the growth rate of the panther population. Then repeat B using Euler's method at a step size of h equals 1. Compare the approximation with the exact answers. So the differential equation dp dt is going to be equal to k, which is 0.264 times the population 1 minus the population divided by the carrying capacity, and the carrying capacity was 200. So that's the differential equation for this logistic growth situation. So that's our derivative. That's like p prime. I'm going to write that down so we'll have it available. So it's 0.264 p times 1 minus p divided by 200. Okay, so let's go to Excel. think I still have an Excel from a previous time, so we might be able to reuse this thing. So let's reuse the one we had before. So the independent variable is t, the dependent variable is p. We have p calc, which we have the equation for. We have p pre-prime, we have delta p, and we have the error. Okay. Our initial conditions at t equals 0, we had a population of 25. And our actual solution, I remember, let me write that down. Let me go back and grab that. Write it down. Was okay, so p is equal to 200 divided by 1 plus 7e to the minus 0.264 t. Okay, so let me just go ahead and plug that in there. So it's 200 divided by the quantity 1 plus 7 times e to the negative 0.264 times t, which is this cell. Close the parentheses, and I should get 25 at t equals 0, so that's good. P prime, okay, the equation we have is equal to 0.264 times p times the quantity 1 minus p divided by 200, close the right parentheses. 264 times b, p times 1 minus p over 200. Okay, so that should be good, right? So p prime is that, delta p is, in this case, we're changing the delta to 1. And we're going to change this equation so it's 1 instead of 0.1. Let's see, p is calculated by taking the old p plus the delta p. Calculation, I'm going to copy down. I copy down both of these equations, actually all three of those. And now what I should be able to do is just to copy this whole thing down. Okay, so, and if I go far, let me just keep copying it down. What we should see at some point is that the thing approaches the carrying capacity. So there's the population. You can see how it's approaching, both in the analytical and the numerical solution. It's approaching 200. So that's the, this is the Euler's prediction. This is the calculated values based on the solution to the differential equation. And what did it say after 5 years? We had a population of 39. Is that right? 2 years. 2 years population of 39. So that was the analytical solution. Gave us very close to it. This is our approximate solution. So it looks like everything is working out. Our population is approaching the carrying capacity. The initial condition is correct. The condition after 2 years is pretty close. Here's 39 versus 38. And it says, at what time is the panther we'll come back to that. Let's just plot this. So we're going to plot these three things. Let's see what this relationship looks like. So we're going to highlight everything, go to Insert, go over here to Scatter Plot, pick this one, and now we're going to go up to Move Chart to make a separate sheet that includes the graph. So there it is. There's our logistic growth equation. You see the numerical solution is pretty darn good. Of course, it matches almost exactly up here because they both have to approach 200. They both have the same initial condition. This is the biggest error is where the slope is the maximum. And you can see the slope's the maximum somewhere about like 8. So we're going to prove that analytically now. So let's switch over. And we're going to do the same thing we did before. We're going to take this equation and take the derivative of that, and that will give you when the population is growing most rapidly. Is that correct? Here's the second derivative. Population is growing. Okay, yeah. So we're looking for this maximum slope of this thing. So let me group those together, copy them, move them to a separate page, paste it in there. Oh, something happened. It's not showing up as copied. Copy. Actually, let's put this on one page. I think that's, sometimes it doesn't copy if you. Okay. Now we'll go to the end, paste it. There it is. So we're going to take the derivative with respect to time of this thing and look for a maximum. So actually I'm going to go back to this arrangement. So we're going to take dp dt. And based on this relationship. So this is, how do we do that? Well, what we're going to do is you have to use the chain rule. So this is the same as 200 times 1 plus 7e to the minus 0.246 t to the minus 1 power. So when you take the derivative with respect to time, the chain rule says you'll get this exponent times 200, so you get negative 200. 1 plus 7e to the minus 0.246 t to the minus 2 power, and then you multiply by the derivative of what's in here. Well, the derivative of 1 is 0. And so what we get for the second term is you get 7 times the exponent, which is, well, actually the derivative of the exponent, which would be negative 0.246 times e to the negative 0.246 t. So we are applying the chain rule here as well. This would be like u. So the derivative of this is e to the u, and then you multiply by u prime. This part is u prime. Derivative of negative 0.246 t is just negative 0.246. So if we rewrite this dp dt, this part goes to the denominator, and we don't even have to worry about it anymore as far as finding a minimum. So we just have 1 plus 7e to the minus 0.264. Oh, I keep doing that. 264 to the minus 2 power. And up here we have 7 times negative 0.246 times e to the negative 0.246 t. So for this go to 0 is when this is a maximum. Is that true? Well, not exactly. What we actually need to do is take the derivative again. I'm just going to see what the book says. Y is increasing most rapidly where y is equal to 200 over 2, which corresponds to 7.37 years. So how do we know that? I'm going to have to think about that for a second. Okay, so I think they got that off of the graph here. We could do the second derivative, but it gets really crazy. So if you look at here, when y is equal to the carrying capacity divided by 2, which is 100, we get the maximum slope approximately. And then you can use that value of y to calculate the time in years. So what we would do is we would go back to the smartboard thing, and what we would say is when p is equal to 100, so we'd say p is equal to 100 looks like it's the highest slope, so what time is that? So we'd have 100 is equal to 200 divided by 1 plus 7e to the minus 0.264t. So that's the same as 1 plus 7e to the minus 0.264t is equal to 200 divided by 100. So that's 2. 2 minus 1 is 1, so we get 7e to the minus 0.264t is equal to 1. Divide both sides by 7, so we have e to the negative 0.264t is equal to 1/7. Take the natural log of both sides. Like that. So we get negative 0.264t is equal to the natural log of 1/7. Which is negative 1.946, and therefore t is negative 1.946 divided by negative 0.264, and we get 7.37 years. Now, we probably could have done it analytically, but I'm going to go with that. It sounds like a good plan to me.